Welcome to our comprehensive guide on chemical bonding for ICSE Class 10. In this video, we'll break down the essential concepts of chemical bonding, making them easy to understand and remember. Chemical bonding is the force that holds atoms together in molecules and compounds. Understanding how and why atoms bond is crucial for grasping more advanced topics in chemistry. Throughout this video, we'll explore different types of bonds, their properties, and real-life examples to help you connect theory with practice. Let's start our journey by understanding what exactly a chemical bond is and why it's so important in the world of chemistry. Chemical bond is a lasting attraction between atoms, ions, or molecules that enables the formation of chemical compounds. This attraction can result from the electrostatic force between oppositely charged ions or through the sharing of electrons. Chemical bonds are fundamental to the structure of matter, determining the properties and behaviors of substances. Without chemical bonds, atoms would not combine to form the diverse materials we see around us. Next, we'll look at why atoms form bonds in the first place and what drives them to interact with each other. Atoms bond to achieve stability. Most atoms are unstable on their own because they do not have a complete outer shell of electrons. By bonding with other atoms, they can share, gain, or lose electrons to achieve a stable electronic configuration, often resembling that of noble gases. This drive for stability is known as the Octet rule, which states that atoms tend to have 8 electrons in their outermost shell. Let's dive deeper into the types of chemical bonds that help atoms reach this stable state. There are 3 main types of chemical bonds: ionic, covalent, and metallic. Each type of bond forms in a different way and gives rise to unique properties in the resulting compounds. Ionic bonds involve the transfer of electrons, covalent bonds involve the sharing of electrons, and metallic bonds involve a sea of delocalized electrons. Understanding these differences is key to mastering chemical bonding. In the next scenes, we'll explore each type in detail, starting with ionic bond. Ionic bonds form when one atom donates an electron to another atom, resulting in the formation of ions. Typically, metals lose electrons to become positively charged cations, while nonmetals gain electrons to become negatively charged anions. The electrostatic attraction between these oppositely charged ions holds them together. Common examples include sodium chloride, table salt. Ionic compounds usually have high melting and boiling points and conduct electricity when dissolved in water. Let's see how this process works with a classic example. Sodium Na has 1 electron in its outer shell, while chlorine Cl has 7. Sodium donates its 1 electron to chlorine, resulting in a sodium ion Na+ and a chloride ion Cl. These oppositely charged ions attract each other, forming an ionic bond. This process not only stabilizes both atoms but also creates a compound with entirely new properties. Sodium chloride, or table salt, is a perfect example of how ionic bonding works in real life. Ionic compounds have several distinctive properties. They are usually solid at room temperature, have high melting and boiling points, and are soluble in water. When dissolved or melted, they conduct electricity due to the movement of ions. These properties are a direct result of the strong electrostatic forces holding the ions together. Understanding these characteristics helps us identify ionic compounds and predict their behavior in different situations. Covalent bonds form when 2 atoms share 1 or more pairs of electrons. This type of bond usually occurs between nonmetal atoms. By sharing electrons, both atoms achieve a stable outer shell. Covalent bonds can be single, double, or triple depending on how many pairs of electrons are shared. Examples include water H2O and carbon dioxide CO2. Let's look at how covalent bonds are formed and why they are so important in chemistry. Water molecule forms when 2 hydrogen atoms each share an electron with 1 oxygen atom. This sharing allows all 3 atoms to achieve stable electronic configurations. The result is a molecule held together by strong covalent bonds. Water's unique properties, such as its high boiling point and ability to dissolve many substances, are due to these bonds. Covalent bonding is essential for the structure and function of countless compounds in nature. Covalent compounds have different properties compared to ionic compounds. They are often gases or liquids at room temperature, have lower melting and boiling points, and do not conduct electricity in water. These differences arise because covalent bonds do not create charged particles. Understanding these properties helps us distinguish between covalent and ionic compounds in everyday life and laboratory settings. Covalent bonds can be classified as polar or nonpolar. In polar covalent bonds, electrons are shared unequally, leading to partial charges on the atoms. Water is a classic example of a polar molecule. In nonpolar covalent bonds, electrons are shared equally, as seen in molecules like oxygen O2. The polarity of a molecule affects its physical and chemical properties, including solubility and boiling point. Metallic bonds are found in metals, where atoms share a sea of delocalized electrons. These electrons move freely throughout the metal lattice, giving metals their unique properties like conductivity and malleability. Unlike ionic or covalent bonds, metallic bonding involves many atoms sharing electrons collectively, rather than in pairs or between 2 atoms. Let's explore how this type of bonding gives rise to the characteristics of metals. Metals are shiny, good conductors of heat and electricity, and can be hammered into sheets or drawn into wires. These properties are due to the presence of metallic bonds. The free movement of electrons allows metals to conduct electricity and heat efficiently. The layers of atoms can slide over each other, making metals malleable and ductile. Understanding metallic bonding helps explain why metals are so widely used in construction and technology. Electron dot structures, also known as Lewis structures, are diagrams that show the bonding between atoms and the arrangement of valence electrons. These structures help visualize how atoms share or transfer electrons to form bonds. By practicing electron dot diagrams, you can better understand the formation of ionic and covalent bonds. Let's look at some examples to see how these diagrams are drawn. Draw the electron dot structure for sodium chloride. start by representing sodium with 1 valence electron and chlorine with 7. Show sodium donating its electron to chlorine, resulting in Na+ and Cl ions. The final diagram highlights the transfer of electrons and the resulting ionic bond. Practicing these diagrams helps reinforce your understanding of ionic bonding. For the water molecule, draw oxygen with 6 valence electrons and each hydrogen with 1. Show the sharing of electrons between oxygen and hydrogen atoms, forming 2 single covalent bonds. The electron dot structure visually represents how the atoms achieve stability through sharing. This method is useful for understanding the basics of covalent bonding. OctetRule states that atoms tend to combine in such a way that they each have 8 electrons in their outermost shell. This rule helps explain why atoms form certain types of bonds and why some elements are more reactive than others. Noble gases naturally have a complete octet, making them stable and unreactive. The octet rule is a guiding principle in predicting how atoms will bond. While the octet rule is useful, there are exceptions. Some atoms like hydrogen and helium are stable with just 2 electrons. Others, such as boron and phosphorus, may have fewer or more than 8 electrons in their outer shell. These exceptions are important to remember when studying chemical bonding, as they explain the formation of unusual compounds. Electronegativity is a measure of an atom's ability to attract shared electrons in a chemical bond. Elements with high electronegativity, like fluorine, strongly attract electrons, while those with low electronegativity, like sodium, do not. The difference in electronegativity between atoms determines whether a bond will be ionic, polar covalent, or nonpolar covalent. This concept is key to predicting bond types and molecular behavior. When atoms with different electronegativities form a bond, the shared electrons are pulled closer to the more electronegative atom, creating a polar bond. This separation of charge leads to a dipole moment, which affects the physical properties of the molecule. Understanding bond polarity helps explain why some substances dissolve in water while others do not. Ionic and covalent compounds differ in their bonding, structure, and properties. Ionic compounds form from the transfer of electrons and consist of ions, while covalent compounds form from electron sharing and consist of molecules. These differences lead to variations in melting points, solubility, and electrical conductivity. Comparing these two types of compounds helps clarify the impact of bonding on substance behavior. Ionic compounds form a crystal lattice structure, where ions are arranged in a repeating pattern. This structure maximizes the attraction between oppositely charged ions and gives ionic compounds their characteristic hardness and high melting points. The lattice arrangement is a key feature that distinguishes ionic solids from other types of compounds. Covalent compounds exist as individual molecules rather than extended lattices. The arrangement of atoms within these molecules determines their shape and properties. For example, water molecules have a bent shape while carbon dioxide molecules are linear. The molecular structure influences boiling and melting points, solubility, and reactivity. Valency is the combining capacity of an atom, determined by the number of electrons it can gain, lose, or share. Understanding valency helps predict how atoms will bond and what compounds they will form. For example, oxygen has a valency of 2, so it forms 2 bonds in water. Mastering valency is essential for writing correct chemical formulas. Some elements can exhibit more than one valency, known as variable valency. For instance, iron can have a valency of 2 or 3, forming compounds like FeCl2 and FeCl3. This property is important in transition elements and affects the types of compounds they can form. Understanding variable valency is crucial for predicting chemical reactions. Coordinate covalent bond, also called a dative bond, forms when one atom donates both electrons for a shared pair. This type of bond is common in compounds like ammonium ion NH4+. The donor atom provides a lone pair while the acceptor atom has an empty orbital. Coordinate bonds are important in complex ions and biological molecules. Hydrogen bonding is a special type of attraction between molecules, not a true chemical bond. It occurs when hydrogen is bonded to highly electronegative atoms like oxygen, nitrogen, or fluorine. These bonds are weaker than covalent or ionic bonds but have a significant impact on the properties of substances, such as the high boiling point of water and the structure of DNA. Van der Waals forces are weak attractions between molecules or atoms. These forces are important in nonpolar molecules and help explain phenomena like the condensation of gases. Although much weaker than chemical bonds, van der Waals forces play a crucial role in the physical properties of substances, especially in large molecules. Bond energy is the amount of energy required to break a bond between two atoms. The higher the bond energy, the more stable the bond. Understanding bond energy helps explain why some reactions require heat and why others release energy. Stable bonds are less likely to break, making the compounds more resistant to chemical change. Bond length is the distance between the nuclei of two bonded atoms. Generally, shorter bonds are stronger while longer bonds are weaker. Single bonds are longer and weaker than double or triple bonds. Understanding the relationship between bond length and strength helps in predicting the stability and reactivity of molecules. Molecules cannot be represented by a single Lewis structure. Instead, they have resonance structures, which are multiple valid arrangements of electrons. Resonance stabilizes molecules by allowing electrons to be delocalized over several atoms. Examples include ozone O3 and the carbonate ion Co32. Understanding resonance is important for predicting molecule behavior. Shape of a molecule or its geometry is determined by the arrangement of atoms and electron pairs around the central atom. VSEPR theory, valence shell electron pair repulsion, helps predict molecular shapes such as linear, bent, trigonal planar, and tetrahedral. Molecular geometry affects physical and chemical properties including polarity and reactivity. Hybridization is the mixing of atomic orbitals to form new equivalent hybrid orbitals. This concept explains the shapes of molecules and the arrangement of bonds. For example, carbon and methane CH4 undergoes sp3 hybridization resulting in a tetrahedral shape. Hybridization helps clarify why molecules have specific geometries. Sigma, and pi bonds are types of covalent bonds formed by the overlap of atomic orbitals. Sigma bonds are formed by head-on overlap and are stronger, while pi bonds are formed by side-on overlap and are weaker. Double and triple bonds contain one sigma bond and one or two pi bonds, respectively. Understanding these bonds is important for predicting molecule stability and reactivity. Let's compare the three main types of chemical bonds. Ionic bonds involve electron transfer and form between metals and nonmetals. Covalent bonds involve electron sharing and occur between nonmetals. Metallic bonds feature a sea of delocalized electrons among metal atoms. Each type of bond results in different properties and uses in everyday life. Chemical bonding is the foundation of chemistry. It explains how atoms combine to form the substances that make up our world. From the water we drink to the metals in our devices, chemical bonds are everywhere. A solid understanding of bonding helps us appreciate the diversity and complexity of matter. Chemical bonding isn't just a textbook concept, it's all around us. The food we eat, the air we breathe, and the materials we use all rely on different types of bonds. Understanding bonding helps us make sense of chemical reactions, material properties, and even biological processes like respiration and digestion. Chemical reactions involve the breaking and forming of bonds. Reactants undergo changes in bonding to form new products. The energy changes associated with bond breaking and making are central to understanding reaction mechanisms and predicting outcomes. Mastering bonding concepts is key to mastering chemistry as a whole. Biological molecules like proteins, DNA, and carbohydrates rely on various types of bonds for their structure and function. Covalent bonds hold atoms together in molecules, while hydrogen bonds and van der Waals forces stabilize larger structures. Understanding bonding is essential for studying biology and medicine. Properties of materials like hardness, conductivity, and flexibility are determined by the types of bonds present. Metals, ceramics, and polymers all have different bonding arrangements, leading to their unique uses. Material science relies on bonding concepts to design new materials for technology and industry. Environmental chemistry studies how chemical bonds affect pollution, water quality, and atmospheric changes. The breakdown and formation of bonds and pollutants determine their impact on the environment. Understanding bonding helps us develop solutions for environmental challenges and create safer, cleaner technologies. Industries rely on chemical bonding for processes like metal extraction, plastic manufacturing, and pharmaceutical production. The choice of materials and reactions depends on the types of bonds involved. A deep understanding of bonding enables innovation and efficiency in industrial chemistry. Technological advancements from batteries to semiconductors are based on chemical bonding. The performance of electronic devices, energy storage, and even medical equipment depends on the properties of bonded materials. Chemistry and bonding are at the heart of modern technology. As science advances, our understanding of chemical bonding leads to new discoveries and innovations. From nanotechnology to sustainable energy, the study of bonds continues to shape the future. Staying curious and mastering bonding concepts opens doors to exciting opportunities in science and technology. Wrap up: chemical bonding is a central concept in chemistry that explains how atoms combine to form the substances around us. We've explored ionic, covalent, and metallic bonds, their properties, and their significance in daily life and industry. Mastering these concepts will help you excel in ICSE Class 10 chemistry and beyond. Keep practicing, stay curious, and remember that chemistry is all about connections, both between atoms and in our understanding of the world.